class. So today we're in for a change of gears. We've spent the last week or so thinking about orders of elements of groups, and now we're going to at least temporarily leave that behind and focus on a different group theoretic topic, which is the topic of subgroups. So this topic originates out of a pretty simple observation, which is the observation that sometimes smaller groups sit inside of larger ones. And we've already seen a few examples of this, like the integers is a group under addition, but those are inside of the real numbers, which are also a group under addition. Or if you prefer multiplication, you could think about the non-zero real numbers R star. Those form a group under multiplication, but they sit inside of something bigger that also forms a group under multiplication, like C star, the non-zero complex numbers. So subgroups are the terminology that we give to this phenomenon. Here's the precise definition. Let's let G be any group, then a subgroup of G by definition is a subset, which I'll usually call H, inside of G, such that H itself is also a group under the same operation as the operation of G. Let's take a look at a few examples expanding on the ones that I briefly mentioned on the previous slide. So if G, for instance, was the set of real numbers, which we know forms a group under the operation of addition, then what I briefly mentioned on the first slide was that inside of there we can find another group. For instance, H could be the integers, and we know that the integers are also a group under that same operation of addition. So I would say that H is a subgroup of G, the integers are a subgroup of the real numbers. Here's another example. We could let G be the non-zero complex numbers, C star, which form a group under the operation of multiplication. On the first slide, I mentioned one group that we can find inside of there. That's R star, the non-zero real numbers. That would be one good example of a subgroup, but just to make life interesting for this example, let me choose a different subgroup. A different subgroup I could choose here would be the set UN. That's the set of nth roots of unity that you met on your second homework. Remember, those are defined as the set of all complex numbers whose nth power is equal to 1. Every element of UN is a non-zero complex number, and on homework 2 you proved that that set does indeed form a group under the operation of multiplication, which is the same as the operation in C star, and so UN is a subgroup of C star. So there's another example. Let's take a look at one more. In this case, let's let G be the set Z6, so the numbers 0, 1, 2, 3, 4, 5, which we know form a group under the operation of addition modulo 6. I claim in this case that the set H that consists of just the numbers 0, 2, and 4 is a subgroup of G. But now that's not totally obvious. There's something that needs to be checked here, which is that this set 0, 2, and 4 really is a group under the operation of addition modulo 6. Towards that end, there's the 4 usual things that we need to check. We need to check that H is closed, the operation is associative, there's an identity, and there's inverses. And for at least 2 of these, I think my best recommendation is actually to make a table that shows us how to combine any 2 elements of H under the group operation. I've made that table off to the right for you. Remember that the group operation here is addition modulo 6. And so now if I ask, how do I know that H is closed under the operation? I can say, well, look at the table, and you'll notice that when you combine any 2 elements of H under the operation, you get another element of H. How about associativity? Well, okay, we never really check associativity, so you might be tempted to just check it off. But, I mean, in this case, I can actually say something a little bit better, which is that if you believe associativity is true in G, then associativity is true in H as well, because associativity is a statement about the operation. And so if we knew the operation was associative from our understanding of G, then it must be associative also in H. How about the identity? Well, the identity, because the operation is addition, is 0, and 0 is an element of H, so it's got an identity element. And lastly, how about inverses? This isn't totally obvious, but again, it's something that we can say see table to verify, because for any given element, for example, the element 2, we can see from our table that there's something I could combine it with that would give me the identity, namely 0. So this checks that H really is a group under this operation, therefore it's a subgroup of G. I want to take a moment now that we've looked at a few examples to highlight a non-example to stress the point that it really is crucial in this definition that G and H have the same operation. So as a non-example, I could let G be the integers, which is a group under addition, and I could let H be the set Z6, which is a group under addition mod 6. Now, technically, Z6 is a subset of Z, because Z6 is the numbers 0, 1, 2, 3, 4, 5, which are a subset of the set of all integers. But Z6 is not a subgroup of Z. And the reason is that they have different operations. In the integers, the operation is plus. In Z6, the operation is plus mod 6. Or another way to say that same thing is that depending on whether we're thinking of two numbers as elements of H or elements of G, we'll get different answers when we combine them. Like 3 plus 4, if we're thinking of those inside of H, which is Z6, we'll get 7, which we then have to reduce to 1 in order for it to be an element of H. Or if we were thinking of those as integers, then when we did 3 plus 4, we'd just get the integer 7. We wouldn't get the number 1. So these are two different answers, which is again highlighting the fact that these two groups have different operations. The last thing I want to say for this video is that there's two kind of boring examples of subgroups. Two answers that you could always give to the question, hey, here's a group, can you find a subgroup inside of that? And that's that if G is any group, you could let H be the set that only contains the identity. That's a subset of G. Or you could let H be all of G, which is a subset of itself. And you can check if you're interested that those are both examples of subgroups of G because they're both subsets that are technically groups under the same operation as the operation of G. Because these examples are a little bit boring, I'll sometimes want to exclude them from consideration. And so I want to give you a little bit of terminology that I'll use if I don't want to consider these examples, but I instead want to consider the richer sorts of examples of subgroups that we saw earlier in this video. We'll say that a subgroup H inside of G is proper if H is not all of G. And we'll say that a subgroup H is non-trivial if H isn't just the identity. It contains more than just that. So using this terminology, I'll sometimes, for instance, by the way, you might see something like this on your exam, which is coming up not too far in the future. I'll sometimes ask you for a proper non-trivial subgroup of a particular group G. And so the way to unpack that is that I'm asking for you for an example of a subgroup of G, but I don't want you to take the easy way out and choose one of those boring examples of a subgroup on the previous slide. I want you to give me an example of a subgroup that's more interesting than one of those. So that's it for today's video. We'll play with some more examples and non-examples of subgroups in our worksheet for today. So I'll see you in class.